Yes, so let's continue how to get our wave equation going. So we had this kind of naive approach of just doing a simple approximation, but we can do a better approximation. So the problem here is that our method is second order in time and second order in space, whereas our starting, guess or just kickstarting the wave equation will only be first order in time, and then this will be a continuing error. So the other approach is to use Taylor. And I will also remind you of the initial conditions. So we had this u of t, x0. We have also a starting, starting state of the system defined by this function f. So Taylor. Well, we have u of xi and t just 1. This time, not any j's. And Taylor, this will be u xi 0 plus, because t1 is just, 0 plus delta t. Delta t dt u plus t squared over 2 faculty dt 2 u plus t power of 3 factorial dt power of 3 u of xi mu j. And again, this mu j is from 0 to t1 in our case right now. So then we assume that the second derivative exists. We just assume that this is a thing. Then we will have that dt squared u of xi 0 equals dx squared. So this again is just a wave equation. At xi. So this f here is this one. So we just assume that we can differentiate it twice, which should be a pretty okay assumption. We shouldn't have, there's very few edge examples with physical meaning where we can't differentiate a starting state twice. Yes. And we can then approximate this. So we will get u of xi of t1 of xi 0. Well, first we insert this in the wave equation. Let's see, dtu I of 0 squared delta t over 2 factorial xi. So here I've basically gone from, let's do the correct one now. Yes, this one. It's this one. It's this one. Well, we need to see as well. It's this one, and then we just insert it here by just using the wave equation. And then we have this error. T power 3 factorial, and I'll just skip the things there. Yes. Then we can approximate this using central difference. And we get, well, pretty much the same thing, only that this time we can xi 0 plus delta t g of xi. That's our starting condition, plus c squared t squared over 2 factorial, or just 2, f x plus minus 2 fi plus fi minus 1. Yep, like so. And then yes, we have also one more. So this one is of course also equal to fi. And we get that our results will be can I use just one line for this? Let's see, u of I1 equals minus r squared fi plus, so if you remember how I defined r was defined, well, r squared c squared delta t squared over delta x squared. So as previous this lecture, plus squared over 2, because 2 factorial there, I plus 1 and you can see how this resembles the numerical solution of the wave equation, only that we've actually been able to use the initial conditions. And this will be more accurate as well. So it's a bit more work to get the right solution, and it also looks more so, I mean, it's not wrong per se, but it will give you more error if you solve the first time step like this instead. Then you will get less error, as you see here, the time step. I'll also show you an example where actually decreasing the time step and spatial steps, or well, grids, will actually be detrimental to your problem. But these are very special cases. But first we'll talk about stability of this method. Also on Friday I will start talking about stability and convergence, like in general for both PDEs and ODEs. So partial differential equations, which we're doing like now, and ordinary differential equations. And then I guess the last 15 minutes, I'll try to explain the projects and how we are supposed to solve them. So, stability for this method. So we also have, so first, in finite differences, we will always have some error in the derivative, the approximation of the derivative. The thing is that we want this error to not accumulate. So if this error is of a certain magnitude, so of a it will accumulate. This basically means that you do some error and sometimes you're able to correct some of it in your next step. But if it's too big, then it's just going to grow and grow and grow. And then you will kind of get an exploding solution. Or using more proper terms, it will tend to infinity. So your solution will basically just become crazy, to use a less formal term. So I can write this as well. If this happens, your will tend to infinity. Which basically means that if you just let it run and it just accumulates more and more error, and it would just give a nonsensical answer, and that nonsensical answer will often crop us as infinity, or in MATLAB also NaN, like not a number. So you can actually calculate the theoretical stability of certain algorithms, but that is outside the scope of this this course. So I'll just mention it. So for the wave equation, we need WEQN. So for the wave equation, we need that this R. So this R, which is equal to C delta T over, that's a delta T over delta X, should be 1 or smaller than 1. This is sometimes called the CFL criterion. And if you're interested in this topic, then CFL stands for Courant Friedrich Levy condition. Just names, basically. Let's see. Courant Friedrich Levy. They have a interesting article on Wikipedia. Yes. So how do we fulfill this criteria? How do we make sure that this is less than 1? We can't really do much about the speed in the medium, so we have to pick these delta t's and x's in a way that this expression is less than 1, or it can actually be 1 as well. So I will then briefly show an example, but I need space on this side.
Excuse me?
Yes?
The delta x squared there.
Where?
When we put our r in our equation.
Yes?
Yeah, should be delta x.
Over here, you mean?
Yeah.
I guess it could be, yes. Let me just double check. Yes, it comes from the approximation. So it comes from here. So there should be a delta x there as well. Let's see. Yes. Delta x squared. So this delta x squared comes from the approximation of this derivative, as somebody mentioned. I just forgot to write it down here as well. But it's, again, included here in this R. Yep, so then we'll show an example. We have, again, the wave equation, UTT equals 4UXX, which means that C equals 2. We want X to go from 0 to 1, and T to go from 0 to 1 as well. Then we have initial conditions, 0 T equals U1 of T. So this is analogous to what we had in the beginning. It should be 0 for all T. And then we have U of x0 equals sine of pi x. This is our f function, as we previously said, for all x. My t's are not good. And then the derivative 0, we will say that this is 0. This is our g of x for all x. And then I just tell you the analytical solution of this problem because we will compare it to it. So that is u of x t equals sin or sine pi x cosine of 2 pi t. And in my example, I will use delta x equals 0.1 and delta t equals 0.05. Oops, that's a weird 5. This results in r equals to 1. So, do you think this will be an accurate solution? Looking at the criterion, we need r to be less than or lower, well, 1 or lower than 1. See, come on. So you think that this will actually be very accurate when this is 1? Well, we'll see. So first, just briefly explain what I'm doing, because we should have it clear. So this is my f. So this is the same as is on the blackboard. G is just 0. You can't use Greek letters, so I'm going to call it dx is 0.1, dt 0.05, and c is 2. And then the endpoints is 1, and the t endpoint is also 1. And then I calculate how many points we have. So that is basically the length of your interval plus 1, because you always have a starting point and the last point should also be the same. Just creating the vector, calculating r, and outputting the value of r. Initializing the vectors, so I'm going to save every time step if you don't want to do this, then you need to at least save, well, the previous one, so that's 1, at least. And then I'm trying to make slicing again. So this is just a list of the inner values of my x. So this goes from 2, which is the second value, and I noted that it has the length of an x, which would be the last value, so -1 will just give me the inner values of my domain, which is why I'm doing like this. And here you see, in order to start the function, I'm using these f values. So basically how it's done in the, well, the second solution I showed. Then we run the time steps. So here it's kind of implicit a nested for loop, but I'm using slicing, so I don't have to worry about it. It also makes for a lot of cleaner code. So I can basically just tell it that I want u of I and then j plus 1. And then it will know that I want only the inner values, and I'm going to calculate the next time step. And again here and here. But it can take some while to get used to this slicing instead of using nested for loops. Well, explicit nested for loops. The reason why I've transposed these is just, well, conventions. So we can also do it without, but then you would have to do some other stuff. So this isn't really important that I've done this. And then u true is the true solution. And we try to run this. So we see that r in this case is just 1. So it's at the upper limit of what it can actually be. Looking at the numerical solution and the true analytical solution, we see that they are fairly equal, fairly the same. If you look at the difference, this might be too small, but you see that it's very low. It's actually too low. So we'll get to this later. But you see, this is around the machine epsilon precision. So what is happening here? Why don't you take a look at it? I'll just prove that if we have a different r, so naively thinking, if you just decrease the spacing, then you should get a better solution. I'm just going to decrease one of them. So now I have a finer mesh. So I have more points to work with. So that means that intuitively it should give you a better result. But if we run this, yes, there we go. So you see, this actually just blows up. Oh, yeah. Okay, because dx is too low now. So see, now r is too high. This is my numerical solution. So this is just exploded. This is 10 to the infinity. So this criterion is violated completely now. It's supposed to look like this, but you also see 10 to the power of 35. So this is just exploded, and the error will just be the same. So I did this the wrong way. If I decrease the time step, then I should have an r of 0.1. Let's see. So now I have an r of 0.1, which intuitively should be better. Well, where's that's a numerical solution as well. It looks the same as the last time. There's the analytical, but you can just peek at the here. So here you see that this is of order of magnitude 0.01. So this is a lot worse, actually. This is a lot worse. So why did this actually work? Any suggestions? Why did actually using the upper bound of this R value give me a better estimation? Or better numerical routine? This is virtually no error. if you actually try to type apps of 1, then you see this is of the order of 10 to the power of minus 16, which is the same that this arrow is showing. So, oops, I'll try to explain what is happening here. And although this is a pretty neat observation, it's not applicable in all cases, I'm afraid. I mean, you could try to study it for every time, but then you would need to change your grid spacing depending on your medium. So the thing is, here we have a homogeneous medium, so we can do more. We can do many more assumptions, but we will just look at the discretized wave equation. So again, uij plus 1 minus 2uij, well, not finished, plus uij minus 1 delta t squared minus c squared I plus 1 j ij minus 1 j divided by delta x squared again. But this time we're mostly interested in the error. So this is the 2 I forgot last time. Yes. Over 4 factorial delta t squared dt 4 u of I t j. So now usually you see a mu here, but since I'm now including all of the terms, I don't need this mu. Then I can just evaluate it at the point, because then this equation will still be upheld. So minus c squared delta x of 2 dx 4 mu of xi tj, that's 1 plus 1 over 6 factorial. Also need this, yes, delta t squared dt, no, power 4, yes, power 4, power 4, 6 u minus c squared delta x power 4 dx power 4 and u, and so on, like this. So, but again, looking at the wave equation, so like we did earlier, we see that if we look at delta t squared dt 4 of u, so now we're looking at this term. We see that we can actually evaluate some of it. dt power of 2. So 2 of these should be c squared dx squared of u. So this is because, according to the wave equation, we have that equals c, or I mean equivalent, as I've been writing it, t. This basically means the same. This is just notation. So what I've done here, I've just taken, well, two of these and said that, oh, well, this is the same. The equation tells me that this is basically the same. So we then get c squared after t squared dx, and then a new round, dt view squared delta t dx squared, and then we can again evaluate this, by using just the wave equation, and we should end up with c squared dx view. So this then is equal to c to the power of 4 delta t power of 2 dx power of 4 u. Yes? Does that make sense? We just apply the wave equation twice now. So we have that delta t squared dt4 of u is the same as this thing. And then we will use the fact that r equals 1. So we have also that r equals 1, meaning that squared delta t squared divided by delta x squared is 1. Using this, we get that delta x squared c squared delta t squared. Gonna underline this. Yep. So then we can look at just this. And we see that, oops, I'm going to use more space, delta t squared dt, well, 4u minus c squared delta x squared dx 4u let's do it like this. This thing is equal to, well, if we take this one outside, we will get c squared delta, delta t squared, no. Delta x, yes. Delta x squared no, this delta t, yes. C squared delta t minus delta x squared dx view. And then you see, since these are the same, this one is 0. Well, I'm not on an O, it's 0. Like so. And what happens now? Well, the error just simply disappears. So if you want, you can try to do something similar with the next term, and you will see this one also just disappears. So in the case of a homogeneous medium, well, you can actually eliminate the error or the approximation error. Though it's not, I mean, it's not generally applicable, but in some cases, this can actually improve your numerical simulations a lot. Like, a lot, yes. So the only error we have here is in the floating point operations in your computer. So we're using double, and double in MATLAB has, well, this amount of precision. So, well, that's the best we can do. I mean, we can't invent new computers just to solve the wave equation. Any questions about this, or did that look okay? Kind of cool? I think it's cool. So, as I hope most of you have already learned, or well, read, there was no exercise hours this Monday. It's instead moved to tomorrow at the same time, so that's 5 till 8 and P10. So there's going to be an extra exercise hour. A question about this, or no? Yeah, I mean, I could start talking about convergence and stability in general for ODEs and PDEs, but I think I will start on this on Friday instead, and just rant a bit about the project. So for the project, I was thinking you should solve. So I'm going to give two problems. One problem will be solving the two-dimensional wave equation, both the acoustic and the elastic one. This means that you will actually have to learn how to derive the elastic wave equation yourself. I will give some hints on the project, and the other task, I have to double check that it's actually possible to get results of this, but you will have to solve the two-dimensional diffusion equation in a porous media. And you're not supposed to solve a two-phase flow problem or anything like this, but it can show you some insight into what some people are researching on this house. For instance, I think it's Bahadur who's researching nanogels that are supposed to block high flow pores. So then you can see the effect if you actually block these high flow pores, then it can get more oil out. Because if you look at a pore system, like so, let's see. So if you have just blobs here, let's see, like so, I guess. And then you have a smaller one here. Then you will have that most of the flow will actually go through the larger pore. And if there's oil inside here, it will just sit there because you need some kind of force there as well to let it loose. So if you then are able to block this pore with some kind of rock, for instance, then the new flow will go through here and also get some oil with it. So I'm going to see if it's possible to actually simulate this in a good manner. Then this will be the other project. So you can pick between one of those. And I won't answer emails. If you send me an email asking about the project, I won't answer this. You will have to ask me on Slack. I'm going to create a new channel for the project. So I want you to, instead of sending an email, you ask the question in this channel. Because if you have this question, then I'm sure that a lot of you also have the same question. So that saves me some time, and you can also see what other people are discussing, or what I want to. Or what I wonder about. You can also create your own groups there and do collaborations using Slack, which is kind of the point of it. So yes, I'll give a more detailed project description on Friday. then we have 30 days to finish the project. Yep. So unless there's any questions, then you're free to go.